It's hard to overstate the importance of salt. It's the basis for the wonderful diversity of marine life. We know how important it is for food and to keep ice off the winter roads. A very long list of the impact salt has on the world around us could be made, and one item on that list would be the curious relationship of salt and hydrocarbons. In this video, we will explore this relationship and learn that a swimming noodle can help us understand why salt is important to oil accumulation.
Hello, I'm Myron Cook. Isn't our world amazing? There are so many fascinating and astounding things about it. One of our joys in life is the process of discovery and solving mysteries that we encounter. Geology is full of mysteries. Many of them have been solved, but there's essentially an infinite number of them that have yet to be solved. That's what I really enjoy is going out to outcrops of rock, hiking up to them, and within a few minutes I can find a mystery that is yet to be solved, and you can do that too. Which brings us to the mystery of this video, this curious relationship between salt and oil. Billions upon billions upon billions of barrels of oil directly associated with salt. How could that be? Well, I thought it'd be fun to send a note out to my fans and ask them what they thought, and I got some really great feedback. Let me read just a few to you. Rob Clausen, 3185, says, my guess is that the salt helped in breaking down organics into a crude petroleum. And Master X 72 says, my guess would be that the oil is from deceased sea life and salt would be present because the seas receded, leaving both behind. And Guy Martin says the salt forms caverns, which the oil ends up pooling in. And then I have B. Graves say, salt forms quickly relative to other hard minerals, and it can form hard encasements that trap and contain oil as it cooks, maybe kind of like the skin of a pie. So some really great comments, and I'm sure they had fun just brainstorming, thinking about it. And that I really enjoy that brainstorming part. But then comes the next phase, and that's gathering information to try to determine what really is the cause. And do our guesses and our brainstorming make any sense? So to do that, we need more information, don't we?
Salt formation begins its journey on land, where rain weathers and erodes the rocks, releasing minerals such as sodium, magnesium, potassium, and calcium into the streams and rivers, which carry them into the oceans, giving us salt water. The same process occurs in playas or dead lakes with no outflows. Focusing on the oceans, where most salt is deposited, there can be regions that have poor circulation, and if it's in a hot, arid region, sodium and chloride ion concentrations become so high the water becomes supersaturated, and the precipitation of salt occurs, slowly building up a layer of salt and other evaporites like gypsum. A great example of a restricted ocean that occurred was about 170 million years ago in the Middle Jurassic during the breakup of Pangaea. Large amounts of salt were precipitated throughout the seaway, including a layer of salt up to 4,000 feet thick in the Gulf of Mexico. That's just hard to believe, isn't it? The formation of oil starts right here with mostly microscopic plankton. This community of microorganisms includes phytoplankton that are photosynthetic single-celled organisms like algae, and zooplankton, which are very small animals like crustaceans and are weak swimmers. These plankton are very abundant in our oceans, as shown here by these huge algal blooms that we are familiar with. In relatively rare cases, regions of the ocean have an anoxic layer of water at the bottom. With no oxygen present, all the plankton that die and fall to the floor are preserved, slowly building up organics mixed in with the accumulating mud. This dark-colored shale will become a source rock for oil as it becomes deeply buried and heated. A layer of shale with just 5% total organic content is considered a good source rock, and one with 15% is considered to be exceptional. Source rocks typically are a dark color because they are carbon-rich. One might ask, how deep and hot does the source rock need to be to generate oil? Well, there are two parts to this process. As the organic material is buried, it undergoes chemical breakdown and compaction to form kerogen, which is organic material that's insoluble in most solvents. These are scanning electron microscope images of kerogen. Notice the magnification values here. With continued burial to typical depths of say 6,500 feet to 13,000 feet or so, and temperatures ranging from about 150 to 250 degrees Fahrenheit, the kerogen converts to oil which is expulsed out of the source rock. With more burial and heat, the oil within the source rock is cracked to natural gas.
I have right here a nice oil sample, very black indeed. Let me show you. It came from here in a field in Wyoming. It's relatively low quality. Some oils are kind of a light color, like the oil you'd put in your car. Some of them even get a beautiful light green color. But when I think about this sample oil, I'm thinking about the plankton that lived and died so long ago to eventually become this very sample of oil. And they lived during the Permian period, some 280 million years ago. We've learned a fair bit about salt and oil formation, but I think we need to learn one other simple yet important attribute of oil. I have this contraption I've made here. It's a model, at least for part of the petroleum system. Let's look at the components. I have a glass pan that's about half full of water. I took this big jar, filled it full of water, and put a glass pane under here, under the jar, got it in here and slid it off and all this business. And propped it up on 3 small blocks of wood right here. And now the water can't flow out because the air can't get in, so it creates a vacuum on the little air bubble here. And for this part here, I have a hiking bladder. Hikers use it to, to keep hydrated with the tube running, and I have it right up under here. And importantly, this bladder, I'm going to put some oil in it. Some green cooking oil, and then I'm going to use gravity and squeezing it, squeeze it down this tube, and let's see what happens. So I have my dyed cooking oil that I've got in here. I've created a bit of a mess. I've never done this before. This is going to be a bit interesting. I hope it's one take. So I got it in here. I'm going to put the hose in here. I've got a little oil that I've been playing around with trying to get this in here. Get it under here like so, and now use gravity. And let's see, bit of a mess. I'm going to have some work to do here. But let's see what happens. Here we go. Cooking oil everywhere. Bubbles from the air hose coming in, or that were in the hose, I should say, coming in, and now oil starting to come and rise up just like the air was. Yeah, what a fun mess. And the oil, as it comes up, it's less dense, or lighter than water, so it's floating up, and it displaces the water, out of the jar. And displaces it out to the bottom. That's called buoyancy pressure. And also the contact that we see forming, I'll try to do this a little faster. That's kind of cool. This is fun. Oh boy. But the contact between the water and the oil that we see, it's quite a sharp line there as we look closely. That's referred to in nature, geologists call that the oil-water contact. So this buoyancy pressure is steadily displacing the water out under the jar here, out into this pan. And I'll just keep it going. Okay, I've created some mess here. This is going to take a while to get this cleaned up. But I have a nice oil-water contact here. If I had more oil in here and this went as better, I didn't think I would leak this much oil. It would displace this oil on down and keep going, this oil-water contact. And eventually, if I had enough oil, it would displace all the way down, and then the oil would start coming out underneath and leaking out underneath into the pan, of course. So this occurs in nature. Now, of course, we don't have glass, but we have other types of rock that can act kind of like this glass, like a seal. And we'll get into that here on the whiteboard. to my handy whiteboard. This is a cross-sectional view of the Earth here. I've got my tree. This is the surface of the land. I could have a house out here, etc. But we see deep underground. And this is a basin where the layers of rock have gone deeper and deeper, and I could continue it on out even deeper. And as these layers of rock have been folded up here as it's coming up out of the basin, these layers of rock rising towards the surface. This is a fairly typical scenario in sedimentary basins around the world. The layer I show here in red is a source rock. Above that, the next layer I want to point out is this dark layer with some black dots in it. This will be our sandstone that has lots of pore space in it for oil to accumulate within. And above that, I have this blue layer, and this represents salt. Now, it's often also gypsum. So gypsum and salt go together. They form from the evaporation of seawater. Another point I want to make that's very interesting and important here in our story is that all this rock, all these layers, those that can hold water anyway, are saturated with water. Almost always seawater, salt water. And in fact, let's take this layer of sandstone here. It would be full of seawater that's as old as the sandstone is. So in this case, we'll say it's 150 million years old. It has seawater that's that old. And it's kind of fun to think about that if you go to the right layer of rock, you can extract water from it, and it's the same seawater that the dinosaurs walked around in along the shoreline. That's fun to imagine. And it turns out that everything below the water table, so we're familiar with water tables. We often drill to them looking for water for homes, especially if you live out in the country. It's fresh water near the surface, but everything below that is saturated with water, mostly seawater. Another way to think about it is there's no such thing as airspace. No air in the pores down here. It's all water or hydrocarbons like oil. Now let's imagine the path that oil takes as it's being expelled from this source rock out in the basin. Here it's hot and it's under a lot of pressure, this source rock. It generates oil, it's expelled from the source rock, and that oil starts working its way up slowly because it's more buoyant than all the water that's filling these layers of rock. But it encounters barriers, and that forces it to start moving up dip, upslope, laterally. So here it goes, up, up, up. Hits this salt layer, can't go through it, and there we go. The salt is a spectacular seal.
Salt is a tremendous seal for two main reasons. First, there are no pores within it, and therefore it is very impermeable. There are just no micropathways for fluid to flow through. Secondly, it can get severely deformed and not fracture or fault. Fractures and faults, of course, provide conduits for fluid flow and destroys the integrity of a potential seal.
At any rate, in this case, it comes up and it gets trapped in this fold. It can't escape, much like the jar that we saw in our model. It starts filling this structure here, and you create an oil-water contact. It turns out that 99.99%, I don't know how many nines I'd go out there, the vast, vast majority of oil leaks to the surface. It doesn't get trapped permanently. And there's whole communities of microbes and things that live off this oil that's seeping to the surface.
Interestingly, in the deep waters of the Gulf of Mexico, bacteria consume leaking hydrocarbons and provide usable energy for large communities of mussels, which live in symbiosis with the bacteria.
When I showed you the model of a petroleum system, or at least part of it, I mentioned buoyancy pressure, and that was important. I think a good way to think about buoyancy pressure is to pull out this swimming noodle that kids love in the swimming pools. Actually, I use them too. They're handy. But I want you to imagine a rigid noodle here, foam noodle, rather than this kind of flexible one. And you're standing in a pool and you start pushing it down in the water. And it just gets harder and harder to push in because you're getting more and more column, I'll say, of this noodle going down, down, down. And the amount of pressure would be many pounds to push down into the water. And that's a function of how tall this noodle is, of course. Well, that's the same thing that happens here. Oil being less dense, can think of the noodle. Now the noodle is really low density, but oil has a density of say 0.8 grams per cubic centimeter, and the seawater has say 1.03. So there is a difference there, not a lot, but it builds up pressure just like this foam noodle does. And you reach limits to the rock. If it gets too tall, this column, it will burst through the rock. The pressure is just too much. The largest oil column in the world, I believe, is about 7,500 feet. So the density difference between the oil and the water that surrounds this whole system creates this buoyancy pressure. And it's trying to force the oil up through the rock. And it usually does. I mean, you just have too much pressure, even if it's a really slow leak. But salt is a super seal. Salt and gypsum, these evaporites, they're super seals. So they can retain more of this oil and you can have a larger oil column. But it doesn't matter how strong the rock is or how good the seals are. If you have a really large structure and you start accumulating a lot of oil column, it'll literally just break the rock and force its way right up to the surface.
Although evaporites are the best seals, shales like we see here are the most common, making up about 75% of all seals. In very rare cases, an impermeable limestone can form a seal. There is something quite unusual and interesting about the oil sample I showed you earlier. As I mentioned, oil steadily works its way up and out of the basin, often moving laterally and sometimes great distances. Well, this oil migrated a very long ways. It started its journey in a basin in Idaho and worked its way into the Bighorn Basin, a distance of some 100 miles or even more.
I've had a lot of people ask me about salt domes and how they're associated with oil. And my sketch here certainly doesn't show a salt dome, so what's going on there? Well, it turns out there are different types of seals. So I'm showing here what's referred to as a top seal. This layer of salt sits right on top of the reservoir, and it prevents the oil from going up like that, and we refer to that as a top seal. To get into the salt domes, I want to show you another sketch. My cross-sectional sketch of a big old salt dome. It's rather obvious, isn't it? Big bulb here, red check marks representing salt. I do show a column of salt underneath it. This salt is feeding up into this dome when it was created and as it is being formed even today. And I can't get into it now, but the process by which they form results in layers of rock that are upturned into the dome, sweep up into the dome. And speaking of these layers that are sweeping up into the dome, I depict sandstones with these dots here, and this layer, and then this one, and these two over here. All the other layers we'll have as shale, which is very common in the Gulf of Mexico. And I also show the horizontal green here. That's oil filled up in these layers of sandstone. Now we've talked about top seals, salt with top seal, but here it's a lateral seal. So the oil is going up these sandstone beds, working its way up, migrating up the sandstone bed, and comes to the seal of the salt against the sandstone. And it's a lateral seal. And it's stopping the oil from going on out to who knows where. The top seal that sits on top of these sandstones in this case is shale. So we have a top seal and a lateral seal in these oil accumulations. And that's how you get this oil accumulated against salt domes. I'll also mention that these reservoirs that I depict here as sandstone. You might wonder, what percent of the pore space do you have? Well, 10% would be typical. It can get up to 25%, 20%. Actually, in the Gulf of Mexico, 20% or so is pretty common, which is very good reservoir. It seems that the more we learn about the world, the more questions we have. And spending time in the great outdoors, making observations and wondering about the deep history, it can be really fulfilling. At least I think so. And to think about all these ancient events that have occurred to bring us to this modern world that we live in, it's nothing short of astounding. I hope you've enjoyed this video. Thank you for watching.